Let's start. So, hello everyone. Welcome to our session today. Thanks for tuning in, and it's my great pleasure to announce today's speakers, Rhea and Samuel. Rhea is doing her PhD with Frankfurt at the University of Freiburg, working on efficient and multi-objective neural architecture search, and most nicely that she's also part of our organizing team here, so I'm excited about that. And on the other side, we have Samuel, who as a research scientist at Abacus, he was doing his PhD at the University of Maryland and is working on NAS+HPO, LNMs all together. And I'm very excited about your presentation, which is going to be about bias mitigation. So without further ado, please take it from here.
Thank you, Rita, for the introduction. Hi, everyone. So today, Samuel and me, we're going to talk about our work on rethinking bias mitigation and using AutoML for fair models. A part of this presentation is going to be work from such as O-levels. That is going to be about Samuel's work on using AutoML for fairness in the tabular data regime. So without further ado, I'll start. So next slide. So let's think about AutoML for applications in the wild. And AutoML techniques are generally evaluated and developed on benchmarks. So when we actually go to real-world applications, we face a number of problems applying neural architecture search or hyperparameter optimization. And an example of this is face recognition. Questions like how I design space. These domains often have certain architectures that are known to perform well, certain hyperparameters which are known to be important. So these should feed into the design of your search space. There are some other issues like what are the right metrics to optimize? And this is something we struggle with for this particular problem as well, because there are multiple possible definitions of fairness, multiple metrics. And there's not a single one that one could choose and optimize for AutoML, for example. Next one is which AutoML method or tool do we use? So there are lots of important considerations here. For example, is your problem multi-objective? Do you want to parallelize across resources? Or do you have access to only a limited amount of compute resources? And this will very much inform which tool you eventually use. Another one is there a systematic way to scale the architectural design choices and parameters that you come up with? So for example, can you exploit larger compute, for example, to scale the architecture in a systematic way or use larger data sets and exploit that to improve your models? And this is something that also plays quite an important role. And the last one, and this is one which, like a question which you'd perhaps also have after this talk, and this is quite an under-researched area in AutoML, I believe, is that during the hyperparameter optimization pipeline or architecture search pipeline, are there particular design decisions which lead to the performance improvements in the end? And this very much focuses on interpreting the AutoML process in general. We can move on to the next slide. Yeah. So let me give you a few examples of such applications which would be quite interesting, for example, for AutoML. One of them is definitely hardware efficiency, where you want to find architectures which are efficient to run on a target hardware in terms of latency, throughput, memory allocation, and so on. And you could think of, for example, using neural architecture search in such applications. Another would be adversarial robustness, and this is a lot of work on this is also done by Jovita. So in this application, we do care about finding performant architectures, but we also want to find architectures which are robust to different perturbations, different attacks. Next slide. Another one would be calibration. So this the applications here very much are weather forecast or medical image classification. And here you care a lot about the confidence intervals of your predictions or the uncertainties in your predictions. Another application is trustworthiness. For example, if you want to have an LLM and tune it to be more fair, more trustworthy, then you have multiple facets to your AutoML problem, or you care about multiple objectives. So with this, I would hand over to Samuel to now talk about, like very much in the same time, to talk about facial recognition, which is one of the main domain we work on.
Thanks, Rhea. Yeah. So what's exciting about what our work we'll talk about today is this like real world application of AutoML and hyperparameter optimization, where real world I'm thinking about like the impact on individual people and actual users or people who aren't necessarily who just get like swept up in systems and stuff like that. And so facial recognition is this very broad class of work that I'll motivate and talk a bit about for probably 5 or 10 minutes before going into our technical depth. So facial recognition, broad category of a word that deals with like general face processing algorithms, where face processing would be like generally trying to predict some attribute about a picture of a face. And so you might be trying to predict like facial key points, like where a nose or a mouth is on an image. And there are other forms of face processing algorithms that are maybe more pseudoscientific around predicting emotions or gender presentation or those sorts of things. And so there's a bucket just like, given one face, tell me about that face. There's another form of facial recognition, which is called facial verification, which is given 2 images. Are they of the same person? So this is a sort of like the next more complicated version of facial recognition algorithms. Just are these 2 people the same person? And then finally, really the most complicated form of facial recognition is this facial identification problem, where you have a gallery of images of both images and identities of people, so like names of people, for lack of a better word, and you have a probe image, and then you're asking, is this probe image, who in this gallery set is this probe image related to? And so this type of facial recognition, specifically face identification, is the most complex and also the most pernicious, form of facial recognition that happens in the wild. This is the type of when police departments or law enforcement run facial recognition, often it's around this type of question, facial identification. And so in this talk, we'll focus on face identification, the hardest of all of these, both technically hardest and also like there's the most sort of moving parts going on inside of these systems. And because obviously this has impacts on people, you think a lot about the ways in which these systems have bias or induce bias in sort of larger systems. And so algorithmic bias, generally you have sort of forms of data bias that sort of is around maybe the training data of your system or the way in which the system gets used or the sort of the data that gets fed through the system. And so in data bias, you're either not sampling correctly or you don't have a representative collection of your data or things like this. There's also forms of socio-technical bias, where socio-technical bias is generally thinking about how this algorithmic system that we computer scientists develop gets used inside of the larger social complex of having a human interpret and make decisions based off of these systems. So in the socio-technical bias realm, like I'm just going to put that off to the side, where we'll focus more on algorithmic bias and how it relates to data bias and how the sort of inside of the machine learning pipeline data and algorithms interplay. And obviously the ways in which people interact with those systems is super important. But for this audience, we'll acknowledge that socio-technical bias exists, but we'll focus on algorithmic bias and forms of data bias. In facial identification, there are different types of data bias that maybe you aren't thinking about when you just think of data bias for specific applications. So specifically in facial identification, forms of data bias can first come from the number of identities. So remember, we have that gallery of images. And so in that gallery of images, if there's a very large imbalance between the number of identities between maybe some protected attribute that would cause a form of data bias. So here we have 3 identities of feminine presenting individuals and 1 identity of a masculine presenting individual. And so that would mean if I then have if I'm trying to look for a masculine presenting individual, it would be easier because there's only 1 of them. And that's one form of data bias in facial identification that doesn't exist in other domains. The other form is an imbalance of the number of identity or images per identity. So in this example, we have more examples of masculine presenting individuals than we do of the feminine presenting individuals. And so your gallery then is made up of entirely sort of imbalanced data because of you can have a balance of the number of identities, but the images composed in that gallery could be imbalanced in this particular way. And so when those 2 forms of identity, data imbalances manifest in the gallery in very different ways and can be teased out to have like very different impacts on the way in which the data bias can influence the facial identification process. And this is described in this AIS paper that I have with co-authors. The paper link is up in the upper right, where we talk about the different forms of these data bias in facial identification can cause different sort of observations of algorithmic bias sort of writ large. Thankfully, though, you can, in sort of data bias things, you can even out these disparities. And so what we do in this talk, we'll just make sure that everything is balanced perfectly on the gender presentation category. And so the galleries will be completely balanced, both in terms of the number of identities and the number of images per identity. But this is a very specific form of data bias that can show up in this specific application, just to give you a sense of like how different and complicated this domain can be, and how that can relate to how we think about the harms of these systems. And so facial recognition, obviously, and facial identification gets used in the wild, and the accuracies of these systems can lead to, of these systems used by individuals and groups of power, can lead to false accusations of things, false arrests, very real harms that are felt by individuals right now, right? So like these are still, this is still a contested technology that still gets used. And there's a lot of abolitionist work on making sure that the harms of these systems get mitigated, not proliferated, and all of these things. There's a very prolific work here called Gender Shades, which was done I think back in 2018, and really identified in gender classification this like much more simple domain that there are intersectional harms that can happen with these systems, and that has spurred a lot of work to think about mitigating those harms. Obviously, there's just don't use facial recognition, but then there's also a lot of algorithmic bias mitigations that exist as well. And so talking a bit about how bias mitigations work from an algorithmic perspective, there are generally 3 different categories of bias mitigations, where you have some pre-processing technique, which maybe transforms data before it goes into the model. There's in-processing techniques that change the learning algorithm in some way. And then there are post-processing techniques that try to do something to the predictions. And typically what these bias mitigations are doing is you have some very accurate model. So you start with maybe the best performing architecture or a model of some sort that's very accurate, but it's not very fair at all. And you apply some bias mitigation to it. And what you'll result in is some model that is very accurate, or sorry, very fair, but it's not accurate. It takes some sort of performance hit in its accuracy. So most bias mitigations, both in the field of facial recognition, but also, like larger in the field of sort of responsible AI, those bias mitigations improve fairness, but they come at a cost of accuracy. And the whole paradigm around these bias mitigations is to take a very highly performant model and basically apply a Band-Aid to fix it in some way. And Rhea and I and our co-authors were thinking about how that is maybe like an ill-posed sort of design to begin with. Like you're starting with something broken and trying to fix it. What if we just come up with something from the beginning that has the properties that we're already interested in? And that caused us to think about how the architecture plays a role in fairness properties of these systems, and whether the architecture itself is biased, and if so, how can we exploit that to use different AutoML methods to find architectures which have the properties that we want from the get-go. And so what we do in our NeurIPS paper that we talked about, that we presented as our oral last 3 months ago or whatever, was we did just that in this facial identification paradigm. So the first thing that we want to do is we want to think about and document the ways in which architectures and hyperparameters influence both accuracy and fairness properties. And so we took 29 different architectural sort of principles from this code model code base called TIM, and we ran a bunch of different hyperparameters around the face rec head, which is this very specific face identification and facial recognition thing, but more general ML things like optimizers and learning rates and whatnot. And we had 2 different main data sets of CelebA and VGGFace, and then we benchmarked training all of these models from scratch on these data sets, and then calculated the error of these systems and a bunch of different fairness metrics, the main one being this rank disparity, which is a very specific fairness metric for face identification. And so once we ran all 355 of these different experiments, you can then plot the accuracy or the error on the x-axis and the rank disparity of fairness on the y-axis. And what you might be looking for evidence is if there's this low variance between error and rank disparity, and there's a very high predictive power of error, then you might say that there's really a weak association between the hyperparameters or the architectures and the rank disparity. So really, like, if you're trying to, if our data look like this, then you're able to conclude there's not that much there with the architecture, as long as you're driving and improving the error, then you'll improve the fairness metric. There maybe not be that much there. But if we were to see data that looked like this is all hypothetical, but if we saw data that looked like this, then there's this high variance between across a bunch of different errors. You could then say that there's some inductive bias to these hyperparameters and architectures that maybe we're able to exploit and use some AutoML techniques to find more fair and more accurate architectures. And this paradigm that we see on the right is actually what we found in our results. So these are our main results on the CelebA data set, where here we see that across a bunch of these different error values, you see very high variance in what the rank disparity metric performance is, and that you don't see this like decreasing line that just driving error improves your rank disparity as well, which really shows that there's something going on here about the architecture and the hyperparameter that we could exploit. And if we look at other fairness metrics, this is just what I said. If we look at these other fairness metrics, here there's a fairness metric about the ratio of these ranks or the ratio of your errors. We see a similar trend where there's not this high predictive power of error. And also in the previous slide and on this slide, there's this, I don't know if you can see my cursor, but in the lower left-hand side of all of these plots, there's not an architecture that is both highly accurate and has a low fairness value at the same time. So there's this opportunity to find, hopefully you could find some architecture that lives down in this lower left-hand corner of these Pareto plots. And taking a step back, it really lends itself perhaps to an AutoML techniques, right? So we know that in traditional machine learning, you're finding architectures that are just optimized for accuracy. And from our sort of benchmark experiments, we really see that finding very accurate models doesn't really predict the fairness properties, you're not also going to find more fair models. And so these bias mitigations that apply a band-aid to very accurate models are like just suboptimal from the get-go. And so if we want, we could maybe design fairer architectures from the ground up to begin with. And so we saw on the previous slides the Pareto front of these different fairness metrics, and the highest performing model is this dual path network. And so what Rhea will talk about in the majority of her time talking will be about designing a search space around that and seeing if we can use these AutoML techniques to find a novel architecture that lives in the bottom left of all of these slides. So back over to you, Rhea.
Thanks, Samuel. So before we dive into the details of our methodology, let's start with a recap of multi-objective AutoML. So we often have, for multi-objective optimization, we often have more than one objectives which are to be minimized or maximized. And the solution here is not a single point, but a set of points, which is often called the Pareto front, which captures the trade-off between two different objectives. And what is nice about NAS and HPO algorithms is that they already maintain a population of configurations. So I think they are a very natural candidate for multi-objective optimization. So the examples of this could be, as we saw earlier, latency versus performance, clean accuracy versus robust accuracy, or the plot that we saw earlier, that's rank disparity versus the error rate. Next slide. To give you an overview of the techniques that are prevalent for multi-objective AutoML, the first set of techniques are mostly black box techniques, like evolutionary search based on optimization or reinforcement learning. So these actually can have or support really expressive search spaces. For example, you could have architectures in your search spaces, continuous hyperparameters, discrete hyperparameter choices, and so on. And the search is often very expensive because they often require multiple evaluations of your network. And if you consider applications like face recognition, where the data sets are quite large scale, this can become really expensive. However, some of these methods, particularly the evolutionary ones like NSJ2, are quite performant. Another family is of gradient-based methods. So these methods are based on scalarizations of objectives. These are often applied to very restrictive search spaces, currently mostly architectures. The search here is cheaper compared to black box methods, but these methods are often brittle and not robust across different search spaces. Next slide. So the method that we focus on or we use is Bayesian optimization. And we chose this mainly for simplicity, since we through our analysis, we wanted to establish if we can use the simplest possible technique to get gains over what are the Pareto optimal architectures from our analysis. Yeah. So now let's dive into the details of our search space. So we find out that the dual path network architecture, actually, it was Pareto optimal for both the VGGFace2 and CelebA dataset, and it was highly accurate. So we used the dual path network architecture to construct a search space. So what we do is dual path network usually has a fixed block, and we replace it with a searchable block. So every edge of this block, we have 9 possible operation choices. There are 3 such edges, amounting to the number of architectures in this space is about 729. But in addition to that, we also search for the optimizer type. We have options amongst the Adam, SGD, Adam W. We search for a learning rate, which is a continuous hyperparameter. We also search for face recognition head, which could be cos face, arc face, or Mac face. Then for multi-objective optimization, we actually choose a very simple algorithm, that's Parego, which is based on random scalarizations. The 2 metrics of interest here are the overall accuracy and the fairness metric, that's rank disparity. So we then also use multi-fidelity optimization. because what we observed is a single training run for us would take up to 2 days on a node with 8 GPUs, which was quite expensive. And hence we use multi-fidelity optimization to invest more resources into better performing configurations. We use hyperband here. Next, to sort of chain all of these components together, we use the SMAC3 library. And finally, use Bayesian optimization with the expected improvement acquisition function and random forest surrogate for joint neural architecture search and hyperparameter optimization. So through our analysis, we independently run search on both the CelebA and VGGFace2 datasets. What we find out is that on CelebA and VGGFace2 datasets, we find architectures that lie in the lower left corner of the Pareto front. And that is what we want because we want to minimize on both of the objectives, the rank disparity and the error metric. And the other architectures in these plots are the handcrafted ones from our large-scale analysis, which Samuel talked about. And the observations and the validation and test sets and the transfer was quite similar. And then we take these pre-trained architectures and transfer them directly to 6 different face recognition data sets for both the architectures pre-trained on VGGFace2 and CelebA. Note that we don't fine-tune and we simply transfer the architectures here. So these data sets, most of these don't have a protected attribute. So this is kind of a sanity check to see if our models are performant across these different data sets. And we actually observed that the architectures discovered by SMAC did outperform the different handcrafted ones. And the different handcrafted ones are the ones that lie on the Pareto front from our large-scale analysis. One question that we were very interested in was also how do the fair properties of these architectures translate to different protected attributes? So for CelebA and VGGFace2, we primarily study gender as a protected attribute, but then we transfer to this data set called racial face in the wild, which has race as a protected attribute. And there are 4 different races or groups in this data set. And the metric then transforms to maximum pairwise rank disparity. And what we observe is that without any additional training, the SMAC architectures do transfer quite well and are very competitive in terms of both the rank disparity and the error metric. In addition, we also transfer to another data set that's AgeDB, and that has age as a protected attribute. Here again, we have 4 different age groups, and we compute the disparity across different age groups. That's a pairwise maximum disparity and the overall accuracy. And again, on this data set, we observe that the architectures which were discovered by SMAC outperform the handcrafted ones. We also did compare with other neural architecture search methods, specifically the multi-objective ones. That's MoASHA and NSGA2, and we used SignTune library for these 2 baselines. And what we observed was that the architectures discovered by SMAC were performant across different metrics compared to these baselines. One interesting thing is that we actually optimize only for rank disparity, but what we observed was that the architectures were competitive across like different fairness metrics too. So another question which we have often been asked and what we also try to study is which properties make these architectures fair in the first place. So to study that, we use linear probes. So to give you an idea of what linear probes are doing is we extract the feature representations from last 2 layers of different networks, and we use a linear classifier then to and train it to predict the gender based on these feature representations. So these networks in no way see the gender or are untold about the protected attribute. So we don't want it to exploit the protected attributes that's gender to make prediction for a given identity. And hence we want these the results from these linear probes, to have a lower classification accuracy. And what we see is that the SMAC architectures, in fact, have much lower classification accuracy on gender classification compared to the other baselines. And what this means is that the architectures, the feature representations of it are not exploiting gender as a protected attribute to make predictions for a given identity. So this is like a fun experiment which we did, which is not in the main paper, and this was part of the rebuttal. So and this is like quite interesting to me is so we asked the question of how does pre-training on data sets like ImageNet affect the accuracy and disparity. And we use the dual path network architecture, and we use a pre-trained one from the TIM library. And then we used another one, which we trained from scratch, and then we fine-tuned the pre-trained one on the VGGFace2 dataset. And interestingly, what we see is that, yes, as expected, the one where we are fine-tuning does have a higher accuracy to start with, but the retraining ones eventually starts catching up quite quickly. Secondly, the one which we are fine-tuning starts with a quite higher disparity. And this could be perhaps because of dataset bias or representation issues that exist in the ImageNet. It's a pre-training dataset. But this also is kind of a bit sad, because what this means is that we do have, through Hugging Face or TIM, we have access to a plethora of pre-trained models. But this means that we cannot directly exploit them for example, face recognition, which is also a type of classification task. So it would be very interesting in future to see how we could exploit these pre-trained models and align them to be more fair. Now I would hand over to Samuel to talk about his point.
Let's see. All right. Yeah. So I think the results that we have on the facial recognition data set and application are really promising, right? So we're showing this entirely new bias mitigation technique that works pretty robustly using these AutoML techniques, and so that's pretty exciting just to begin with. But it's just on one domain, and facial recognition is maybe we didn't talk about it here, but we also compared to like the existing bias mitigations in facial recognition, and we beat those techniques. But in facial recognition, there aren't that many bias mitigation techniques. It's as you saw, it's a pretty complex space, and there's not too much work in bias mitigations there. So it's not that, I mean, it's very important to improve upon improve on bias mitigation techniques there, but it's not as a competitive a space. But in tabular data, there's a very large body of work that looks at bias mitigation, and there are standard data sets, and there are very standard fairness metrics. And so if we were able to expand upon the results that we have in facial recognition, doing so in tabular data is the next obvious place to do that. And so what my co-author Rashik and I did was to take the very similar approach that Rhea and I talked about for facial recognition and apply it to tabular data. There are these standard data sets called adult and compass and ACS where there are very standardized and existing bias mitigation techniques, and so it's very easy to benchmark against them. But it's a very competitive space because this field has been around for maybe 5-ish years, like all driving for these specific benchmarks. So we were interested in how this AutoML bias mitigation compared. And so what we did was we set up a search space of common tabular models, particularly on these data sets around MLPs, ResNets, and this model called an FT transformer. And we looked at these three data sets: the adult data set, the compass data set, ACS, American Community Survey. And there are a bunch of different fairness metrics. And so the first question that we had to ask was whether the search spaces had some sort of expressive capability of looking at a bunch of different accuracy and fairness performances. And here what we're plotting is on this one fairness metric of like the mean difference between these groups. For each one of these search spaces, which is a different color, we're seeing a pretty broad range of different fairness performances and also accuracies. And so that sort of led us, this is akin to what I was talking about at the beginning, where we're seeing that there's a lot of room here for an expressive search space for these different fairness metrics and data sets. This specific one is on the ACS data set anyway. And when we look at the results, so we set up the search space, we run the same paradigm that Rhea was talking about. First, we benchmarked everything. So all of these dots are the Pareto fronts for and the best performing models for each one of these different existing bias mitigation techniques, where there's a standard library that you can use to run all of these. And the baselines are these orange plots, and most of these bias mitigations improve the fairness. Some of them also improve on accuracy as well, but they're pretty. Most of them see a performance degradation, like I was talking about at the beginning. But we ran our search space. Oh, the other thing of note here is there are these two plots. They're both on the COMPAS data set. This is on the average odds difference between the protected attributes, and this is on a fairness metric called disparate impact. So we have two different fairness metrics, the same data set. And when we plot our AutoML found new Pareto front, we see we're finding much more accurate models, and at least on the average odds difference, much more fair models as well. So like we're finding the fairest model as well as the fairest and most accurate model. So these Pareto-dominate, and on this fairness metric, we're just being Pareto optimal, but we're still like drastically improving the accuracy and improving performance, improving fairness as well. And so these results, I think, one, show the versatility of our bias mitigation approach, that very simple modifications to the search space in a new paradigm can really find a much more compelling low error and low fairness metric model just using AutoML techniques. And so the things, I think what I'm super excited about is just like continuing on this line of work in using AutoML for different notions of fairness. And so in the future, I'd love to continue this tabular data domain. There's much more work just on what we presented the work at a workshop at NeurIPS. So there's more work just to be done on there. I'm also really excited to expand into other notions, not expanding the concept of fairness, right? So there's traditional fairness notions, but there's also data imbalance is one of the most pernicious problems in tabular data. And it's a very easy sort of mapping between data imbalance problems and these fairness problems. So I think that there's an opportunity here for AutoML and the work that we do in this community to have very big impacts there. We're also really interested in continuing that fine-tuning versus training from scratch work that Rhea talked about, and seeing sort of expanding out that initial observation around the difference between fine-tuning and training from scratch. Rhea, if you want to take over and talk about some other future work.
Yeah, so one of the things that I'm quite interested about is gradient-based multi-objective optimization. So one thing that like often bothered me a bit was how expensive our runs were. We like use about 12 nodes with 8 GPUs over about 15 days, and that was quite expensive. So I'm very excited about using gradient-based methods for multi-objective optimization to make the search very efficient and robust. Another direction that I'm quite interested in is interpretability of architectures, that is assigning different design choices of architectures and hyperparameters to specific gains in metrics. And I think that is like quite lacking in the AutoML community, and this is something I would like to explore it further. Yes, so to conclude, and like, so the biggest takeaway from our work is that architectures have quite a big influence on fairness. And instead of having a fixed architecture and trying to change the in-processing, the pre-processing, and the post-processing pipeline, fair architectures and hyperparameters should be built from ground up, exploiting the knowledge that we gained from our large-scale analysis and using AutoML on different applications. So our code and paper is publicly available if you're interested in details, and we'll be happy to take questions. And thank you for hosting us.